What's up, guys, and welcome to this video. Okay, so this is a new series I'm trying out. Basically, it's going to be called something like concept videos, and basically I'm going to be going through a certain concept. For example, in this video, we're going over gravitational force field. So by concepts, I mean I'm going to break down the definitions, what they mean, do some examples, and hopefully just help you guys better grasp concept. Okay, so with that said, also there's no real format to these videos. So we're going to do questions, we're going to do problems. Most of it isn't going to be typed, there's just a couple type slides. Everything else will be just handwritten. So yeah, okay, so let's get into these videos. Okay, so we start off with the definition for gravitational force field. Okay, so it is the region surrounding a body in which it exerts a force of attraction on other matter. Okay, so if we digest this, so we have to have, firstly, we need to have a body. Okay, so if we start off with some body, let's say it's a planet or something, it's a region of space surrounding the body, so it's around the body, it's all around the body in all directions, which exerts a force of attraction. So I'm going to draw arrows towards this body, just to show that we're having forces of attraction. Okay, which it exerts on other matter. So in order for this field to exist, there must be other matter. So if we place another body there, then it's going to get attracted to this larger body. Okay, regardless of the size, if we have a bigger body, it will also feel a force of attraction because it's in this field around this body. Okay, so let me not do that. Okay, so with that being said, let's see how we draw force fields. Okay, so the closer together the lines, the stronger the field at that point. So if we want to show that there's a very strong force field, we will increase the density of the lines, increase the number of the lines, just to show that the field is very strong. Okay, and then the direction of the arrow must indicate the direction of the field. Okay, and previously we said it's a force of attraction, so therefore the arrow must always be directed towards the mass. Okay, it's always going to be directed towards the center of the mass specifically. Okay, and then gravitational forces are given the symbol G. Okay, so we know this. We even know that the gravitational field of attraction on Earth is given a value of 9.8 meters per second squared. Okay, so that's what we know, and that is our second definition, which is weight, the gravitational force that the Earth exerts on any object on or near its surface. Okay, everyone's experienced that. If you jump up, when you're on the surface of the Earth, if you jump up, you will definitely fall back down. And the reason for that is because of the gravitational force fields pulling you back down towards its center. Okay. Okay, so let's go into an idea of interacting gravitational fields. Okay, so we know that gravitational fields are always directed towards the object. Okay, so if we have two objects, or let's say two planets rather, or two objects actually, could be any object. Okay, they will exert a force on each other. Okay, so because both of these objects want to both of these objects have some mass and want to apply a force field. Okay, so they will exert a force on each other, so they're going to affect each other. So I'm going to draw some lines. Okay, and later on we will find out that it's actually dependent, the strength of the force is dependent on the mass. So the larger the mass, the stronger the force. So for this larger mass, I'm going to draw lots of arrows just indicating the field is stronger, whereas for the smaller mass, I'm just going to draw a couple arrows just indicating that the force field is a bit weaker. Okay, so not too many arrows. And according to Newton's third law, these forces are equal in size but opposite in direction. Okay, so as a result of these force fields being applied at a point, there's a point between two objects where the net field strength is equal to 0 newtons per kilogram, or 0 meters per second. So there's a region somewhere between these two objects where you'd feel weightless. So if you placed a third object, some object in that region of space, okay, so if we place some object in between, somewhere in between here, because it feels attraction, okay, so let's just put it right there, because it feels attraction in both directions, at some point it's going to feel a zero force. Okay, so it's going to essentially feel weightless. Okay, so now I'm going to move on to this nice equation we had before, where we say Newton's law of, okay, so back to this point quickly, we will be able to find the exact point where it feels weightless, but to do that we need to understand Newton's law of universal gravitation. So every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the squared distance between their centers. Okay, so what we're saying is that the force is directly proportional, so it has a directly proportional to the product of their masses, so m1, m2, and inversely proportional to the squares of the distance between their centers. Okay, and we can change this proportion sign to an equal sign if we introduce g, which is the gravitational constant. Okay, so the gravitational constant has a value which obviously does not change. Let's see if I've got that. There we go. Okay, so the gravitational constant has a value which is 6.7 times 10 to the minus 11 newtons meters squared kilograms to the minus 2. Okay, so how did I get these weird units? Okay, so if we start off with F equals G m1 m2 over r squared, now I want to make G the subject of the formula, so I have F r squared over m1 m2 is equal to G. Now I look at the units. The units for force is newtons, the units for radius is going to be meters squared, and the units for mass 1, mass 2 is going to be kilograms times kilograms, which is kilograms squared. Okay, so that's how I get to those weird units. If you forget what the units are in a test, then you will be able to get back to them. Okay, so let's digest this again. So F is our force, G is our universal gravitation, M is your mass 1, M2 is your second mass, and R is the distance between the centers. Okay, and that's obviously in meters. Okay, so we're working with SI units. Okay, let's talk graphs. Okay, so if I wanted to plot a graph of F versus M1, okay, so we discussed this already, that F is directly proportional to the mass, so you have a straight line graph. Okay, similarly, if you plotted F with M2, you'll get the same straight line graph. Okay, because as F equals G m1 m2 over r squared, as my masses go up, my forces go up. Okay, so we have a straight line. Okay, but something different happens when we look at F versus R, which is our distance. Okay, so if we look at this graph, if our R goes up, then our denominator is going up, so that means the numerator goes down, so the number is getting smaller, so F gets smaller and smaller, and also R cannot equal 0, right? Because then we would have the bottom being undefined. So what we end up with is a graph like that, okay, which is expected. It never reaches, okay, it never reaches 0. R can never get to 0, and so F can also never get to 0. So R will always be off of this axis, and similarly F will just get smaller and smaller and smaller, but won't cross the axis. We have asymptotes on these. Okay, and then lastly, if we speak of F versus r squared, 1 over r squared. Okay, so let's look at that. So I'm going to rewrite this formula slightly differently. So I'm going to say that's G m1 m2 times 1 over r squared. Okay, so as my r squared becomes smaller, so as this entire term goes down, my force increases. Okay, so I hope that makes sense. As this term goes down, as this entire term, I'm looking at this entire term, 1 over r squared. So as r squared increases, that side goes down, which causes my force to increase because it's at the bottom. This entire term is going down. Okay, and that results in a straight line once more, where the gradient is equal to G m1 m2. Okay, so we have, if we look at the normal format, y equals m. Okay, so we have mx plus c. C goes to 0 because it intercepts at the origin. M is our gradient, which is this whole thing here, and our x is 1 over r squared. Okay, so with that being said, I think we can actually go into some examples where we actually use these equations. So let's say example 1. Okay, so example 1. Let's say we have a man or a person has a mass of, let's say, 90 kilograms and is 10 meters away from another person with a mass of, let's say, 60 kilograms. Okay, calculate, let's say, question is going to be to calculate the force due to gravity, Fg, that they exert on each other. Okay, so let's say this is person 1 and this is person 2. So calculate the force. Let's say calculate the force that person 1 exerts on person 2. Okay, so we're going to our basic formula, which is Fg is equal to G m1 m2 over r squared. So we know what G is. It's 6.7 times 10 to the minus 11. Okay, times mass 1, which was 90 kilograms, times mass 2, which was 60 kilograms, over r squared, which is 10 squared. Okay, so if we plug this into our calculator, let's see what we get. That's 90 times 60, 10 over 10 squared, and we get a value of 3,618 times 10 to the minus 9 meters. Okay, but it says calculate the force that person 1 exerts on person 2. So remember, forces have got direction. So we're going to say towards person 1. Okay, so now if we look at another question, it says, okay, so it says state, okay, so it says without calculation, state the force that person 2 exerts on person 1, and it says state the law used. Okay, so first of all, we need to actually understand what law we're going to use. Okay, so we're going to use Newton's third law. Newton's third law that says that every object attracts, object A exerts a force on object B that is equal in direction, but equal in magnitude, but opposite in direction. Okay, so Newton's third law can be used to say that so this was 1, force 2 is going to be the same magnitude, 3,618 times 10 to the minus 9 newtons, but instead of towards P1, this time it's going to be towards person 2. Okay, so all that's changed is the direction. Okay, and the law we used is Newton's law of gravitation. Okay, Newton's law of gravitation for question 1 and Newton's third law for question 2. Okay, so if we go on to example 2, okay, so let's say we have two planets. Let's say the Earth has a mass of 5,98 times 10 to the 24 kilograms, and let's say Pluto has a mass of 3,52 times 10 to the 24 kilograms, or let's say 22 kilograms. Okay, and their center distances between the two planets is, let's say 5,9 times 10 to the 8 meters apart. Okay, so calculate FG. Okay, again, nothing too difficult. We're just going to apply Newton's law. So we're going to say G m1 m2 over r squared. Actually, I'm going to change m1 m2 to m of the Earth mass of Pluto over r squared. So that's going to be 6,7 times 10 to the minus minus 11 times mass of the Earth, which is 5,98 times 10 to the 24, times the mass of Pluto, which is 3,52 times 10 to the 22, all over r, which is 5,9 times 10 to the 8. Okay, I'm putting brackets on purpose so that I get everything in the r squared term. Okay, so if we plug this into our calculator, let's see what we get. Times 10 to the 22 all over 5.9 times 10 to the 8. And if we square that number, we get a value of Fg is equal to 4,0515 times 10 to the 19 newtons. And what direction would we say? Let's just say, because we haven't been given anything, we'll just say attraction. Okay, so basically these masses will attract each other. Okay, so with that said, let's go on to a different section which has to do with proportionality. Okay, so the idea with proportionality is we're trying to find a relationship between certain forces where we haven't been given specific values or numbers. Okay, so let's say we have two objects of mass m1 and m2. M2, okay, and they experience a gravitational force F. Okay, when their center distance is a distance of, let's say, r meters. Okay, so in this question, we have been told, or in this breakup of this question, all we've been told is we have mass m1, mass m2, they experience a force F, and their center distance is a distance r away. We've been given no numbers. Okay, so then it says, part 1 of this question says, what happens, express the new force F new in terms of F if. Okay, so if the mass of one object is doubled. Okay, so first we need an expression for the old force. So I'm going to call that F old. And I'm actually going to do it at the top because we're going to go through a number of these scenarios. So I'm going to say that F old, let's use a different color. Let's see, let's use a green. F old, the old force is equal to G m1 m2 over r squared. Okay, now for this next question, F new is going to still be G. Okay, one of the objects is doubled, so I can pick. I'm going to just double m1. So 2 times m1 times m2 all over r squared. Okay, so now I'm going to pull out the 2, so I'm going to say 2 g m1 m2 over r squared. Okay, now if I look at this, g m1 m2 over r squared is the same thing that I have here, which is the same thing as f old. So this is actually equal to 2 times f old. So my new force is 2 times the old force. Okay, so for the second one, for the second question, let's say what happens when or if both masses are tripled. Okay, so now my F new is going to be equal to G. Mass 1 needs to get tripled, mass 2 needs to get tripled, all over still r squared. Okay, so if I multiply that out, I get 9 g m1 m2 over r squared, and again this right here is equal to m old, so it's going to be equal to 9 times f old, or the old force. Okay, so question 3, let's say what happens when the distances is, let's say the distances is halved. Okay, so what happens when the distance is halved? Okay, so this one we have to be a bit more careful. Okay, so F new is going to be equal to G m1 m2. Nothing's happened to the masses, and I've halved the distance. All of that squared. Okay, so actually I have G m1 m2 over 1 over 4 r squared. Okay, so remember, just using some maths, to get rid of this 1 over 4, I multiply this by 4 at the top and the bottom. Okay, so what I'm left with is these two cancel, so I'm left with 4 g m1 m2 over r squared, and if I look at that, that's the same thing as g old, so I'm left with is equal to 4 times f old. Okay, yeah, I mean, that's basically, all these questions are the same. Let's go through one more way we do more than one thing. Let's say one mass is doubled and the distance, the center distance, is tripled. Okay, so if that's the case, I have F is going to be equal to G. One of the masses needs to be doubled, so I'm going to 2 mass 1. I'm going to leave mass 2 as it is, and I'm going to triple 3 times R squared. Again, remember your brackets, otherwise you're going to make mistakes. Okay, so if I multiply that out, I'm left with 2 over 9 times G m1 m2 over R squared, and this is once again my F old, so I'm left with 2 over 9 times the old force. Okay, so it's really not that difficult, quite easy. Sometimes it just scares you because there's no numbers, but don't be fooled. Okay, so let's move on to another example where we speak about the accelerations. Okay, so let's go on to what is this going to be, example 5. Okay, so we have the same situation where the two objects have a mass m1, m2, experience a gravitational force F and their distances are a distance r apart, so the same scenario we had right here, but we want to compare the accelerations. So we want to compare accelerations of the two bodies if m1 has, let's say, okay, so for the first scenario, let's say m1 has triple the mass of m2. Okay, so m1 has triple the mass of m2. Okay, so how are we going to do this question? Okay, so this time we're talking about accelerations. We need to find an equation that speaks of acceleration. Okay, so we all know the equation F net is equal to ma. Okay, so now something we need to understand again is that they both experience the same force. Okay, both objects, remember by Newton's third law, experience the same force. Okay, so all that the acceleration is dependent on is their mass. So if we wanted to get acceleration as the subject, it's going to be F net divided by m. Okay, so we can say that for m1, okay, m1 has triple the mass is equal to 3 times m2, right? So that means acceleration 1, okay, so acceleration for 2 equals F net divided by mass of 2, but acceleration for 1 is equal to F net mass of 1, which is equal to F net divided by 3 times the mass of 2. So the acceleration, if we compare these two, okay, again we're left with the situation where we can find F net divided by m2 is right here. So this can be actually written as 1 over 3 times acceleration of 2. So the acceleration of 1 is a third of the acceleration of planet 2 or mass 2. Yeah, okay, so I hope that kind of makes sense. It's the same kind of situation where all we're doing is we're looking at this F net equals ma as our governing equation, and we're taking note that from Newton's third law, the net force experienced by both bodies is equal. Okay, so now we're going to move on to another example. Okay, all of these examples are very similar. Okay, so this is going to be example 6. Okay, now we're moving on to a question which has some numbers. I'm going to work with a diagram which basically says this. Okay, so we have one planet. Let's call this planet 1, which has, we have 3 objects. Let's call this object 1. Okay, object 1 has a mass of 4 kilograms. Okay, object 2 is going to be a smaller object, object 2, and object 2 has a mass of 1 kilogram, and object 3 is going to be at here, and let's say it has a mass of 6 kilograms. Okay, all of these are acting at 90-degree angles. Let's give them some center distances. Let's say this is a distance of 10 meters apart, and let's say this is a distance of 6 meters apart. Okay, and we're working with that direction being the north, so we have east, south, and west. Okay, so the question that I am trying to answer is calculate the resultant force experienced by the 4 kilogram mass. Okay, so I want the resultant force. Okay, so first of all, I'm trying to understand what direction all of these forces are going to be acting in. Okay, so the 4 kilogram, basically what this question is saying is that the 6 kilogram is fixed. So this 6 kilogram mass is fixed, and this 1 kilogram mass is fixed as well. Let me just 1 kilo. My handwriting, sorry guys. 1 kilogram. Okay, and this 1 kilogram mass is fixed, whereas the 4 kilogram mass is able to move. So the 4 kilogram can move up, down, left, right, however it feels. Okay, but we know that the forces are going to be of attraction. Okay, so the 4 kilogram is going to be attracted to the 6 kilogram block, so that force is going to act directly south. And the 4 kilogram is going to be attracted to the 1 kilogram block, and its force is going to be directly east. Okay, so with that said, basically I need to just determine this force. Let's say this is the force of 1 to 3 and the force of 1 to 2. Object 1, object 2. Okay, so if I wanted to draw a free body diagram of this force, so that's a 4 kilogram. Okay, so that's going to be F13, and that's going to be, I'm actually going to draw it smaller because the force is smaller, F12. Okay, so now that I have that, I'm going to calculate F12. F12 is equal to G M1 M2 over R squared. Okay, so G is 6,7 times 10 to the minus 11. Mass 1 is 4, mass 2 is 1 over R squared. My distance is 10 squared. Okay, so let me plug that into my calculator. Let's see what we get. We get a value of 2,68 times 10 to the minus 12 newtons, and I'm going to say east. Okay, F13 is going to be equal to G M1 M3 over R squared. Actually, this should be R12 and R13 squared. So then we're left with 6,7 times 10 to the minus 11 all over mass 1, which was 4, mass 2 is 6 over the distance, which is 6 squared. Okay, so what we're going to be left with is a force of 4,47 times 10 to the minus 11 newtons, this time acting directly south. Okay, so if we look at these forces, it's clear that force 1, 2 or force 1, 3 is greater than force 1, 2, which is what we expect because the masses the mass of object 2 is smaller than the mass of object 3. Okay, so they want, now we've calculated these forces and they want the resultant force. Okay, so to calculate the resultant force, I'm going to draw another vector diagram just right here, quick, nice and simple. We have that F1, 2, we have that F1, 3. So the resultant force is going to be this force that connects them. Okay, so F resultant. Okay, so F resultant. Okay, so to calculate the resultant force, also I know this is a 90-degree angle. Okay, so to calculate the resultant force, so F resultant is going to be equal to F12 squared plus F13 squared, all square rooted, and that's just from Pythagoras. Okay, so let's calculate that. So it's going to be square root of 2,68 times 10 to the minus 12 squared. Remember your brackets, plus 4,47 times 10 to the minus 11 all squared. Okay, so if I plug that into my calculator, let's see what I get. Minus 12 squared plus 4.47 times 10 to the minus 11 all squared. And if I plug this into my calculator, I get a resultant force of 4,4, let's say 48 times 10 to the minus 11 newtons. Okay, so now the question is, what is my direction? So I'm going to define this as my angle theta. Remember, force has always got to go with a direction. So if I define that as my angle theta, just looking at this, some basic maths would tell me that tan theta is going to be opposite over adjacent. So my opposite is going to be f13, my adjacent is f12, so theta is going to be equal to tan, or the inverse of tan, f13. So f13, let's see, where is that? f13 is 4.47 times 10 to the minus 11, all over f12, which is 2.68 times 10 to the minus 12. And if I plug that into my calculator, let's see what I end up with. Okay, I end up with an angle theta is equal to 86.57 degrees. Okay, so I am going to say the angle is going to be 86.57 degrees, but I'm going to define it like that. So it's going to be what's a clockwise from east. Okay, I hope that direction makes sense. I am going clockwise from true east. Okay, so yeah, so that's just where we have multiple objects interacting with each other. Again, nothing too difficult there. Yeah, okay, so this video is getting slightly long, so I think I'm going to end it there, and we will continue with the rest in another video. So thanks for watching, guys. Stay tuned for the second part of this video.